Okay, perfect. Exponential and logarithmic functions. All right, so then, so I'm gonna start with the exponential functions. So what's an exponential function? Well, it's exponential function. It's just a function of the form a to the power x, where a is a constant. So so exponential functions are functions of the form exponential functions are functions of the form so f of x equals to a to the power x, right? So here you need your a to be positive. So a is a constant. So where a is a positive constant. Okay, so this is really important. A has to be positive. Okay, a is positive, is a positive constant. Okay, different from 1. Right? So we say this is an exponential in base a because the constant here is a. So we say this is an exponential in base a. So this is exponential function in base a. Right? So as I said, a must be a positive constant, different from 1. So for example, I'm gonna probably zoom out a little bit. All right. So examples. So your constant a can be, of course, a whole number, positive whole number. For example, f of x equal to 2 to the power x, right? So then your a is equal to 2. So that's the base. The base is 2. Okay. So this is an exponential function. So this is an exponential function. So it's exponential. Your a can be a fraction, right? It's possible that your a is a fraction. So for example, sorry. So for example, f of x is equal to half to the power x. All right. So then your a, the constant a, would be half. Okay, that would be so the base is half. We say that the base here of this exponential function is half. So this is another example of exponential function, right? Where your a is just is a fraction. It's equal to half, right? So this is an example of exponential function. Your a also could be a decimal, right? A whole number, positive whole number, positive fraction, or a positive what's a positive decimal. So for example, f of x equals to, let's say, you have 4.56713, etc., to the power x. All right, that's another example. So a would be this 4.57, etc. So this is another example of exponential function. Now, so again, so you have to keep in mind, you have this a to the power x. Your constant a is a positive real number, right? It could be a whole number, could be fraction, could be decimal. Now, if your a is 1, so the problem with 1, if a is 1, so f of x, if f of x is equal to 1 over 1 to the power x, 1 to the power x, that will be equal to 1. Okay, 1 to the any power, that's equal to 1. And that's not an exponential function. F of x equal to 1, that's a constant. It doesn't, so the value of the function f here doesn't change, right? It's always equal to 1. So it's a constant function. It's a constant function. So it's not an exponential. So that's why you have to exclude the case when a is 1, right? It's a constant function. Now, if you have a negative, what's the problem with the negative number? So if you have, let's say, f of x equal to, let's say, negative 3 to the power x, this is not an exponential, because a would be a negative number, and the problem is, is not exponential. Okay, so this is not exponential. All right, and this is also not exponential. So your a is here. A would be negative 3, all right? And we said a cannot be negative. And the problem with the negative a negative is that, for example, if you had so why that would be a problem, because, for example, if you had f of half, then that would be negative 3 to the power half. That would be square root of negative 3, and we cannot have negative numbers under the square root, right? So this is undefined, right? So f of half would be undefined. So this is undefined because we're going to have a negative number under the square root, so it's undefined, right? So that's why we have to exclude negative a, all right? And the last, another example of functions. So let's say f of x is equal to x to the power x. So here you have to be careful, because your variable x, it's not just in the exponent, it's in the exponent and also in the base. So your a here, your a would be equal to x, right? That would be your a. But the thing is, x is not a constant. X is a variable. Your input x varies, right? It's not a constant. So this a equal to x is not a constant. So a is not a constant, so that's not an exponential, right? You need a constant a to the power x, but x to the power x is not a constant, so that's why it's not an exponential. So this is not. So it's not an exponential. Okay. So yeah. So then 1 in front of x. What do you mean, Cheyenne? 1 in front of the x. So you mean 1 here? Yeah, I mean, it doesn't matter if you have 1. Yeah, there's 1 there. But the thing is, this power here, this is a power x, but that's x to the power x, right? Even if you have 1 there, but again, for the exponential, you need the constant to the power x. Like you need like 2 power x. You have 1 in front of the 2, but still, it's the 2 which has the power x, right? So so that's why it's not x to the power x is not an exponential. Yeah. All right, guys. However, let me just say there is a very special exponential function, and so there's a very special exponential function when the constant a is equal to the number some number called number e, very special exponential function. So so when a is equal to e, so this e is actually approximately, I think it's 2.7182, right? Then so this f of x, which is a to the power x, would be e to the x, all right? So what's the special about this exponential function when this a is equal to this number e 2.71, etc.? So what's the special about this exponential function is that, and I guess you will see this in Calc 1, I mean, this is just for your information, right? So what's special about this e to the x when the a is equal to this number e is that so the f of x, so then f of x would be equal to its derivative. Okay. Anyway, so you see this in Calc 1, right? So this is called the derivative of the function f. Okay. So anyway, so you see this in Calc 1. Okay. So yeah, but anyway, so this is very special function, exponential function when this a is equal to this number e, right? This is very special, especially very useful in physics. But anyway, so this is just for your information, okay? Anyway, so now next, so that's the definition of exponential functions. Now we are interested in the properties of the graph of exponential functions, right? So properties of graph of exponential. Okay, so again, my function is, so we have this f of x equal to this a to the x. And keep in mind, this is again important, a is positive, right? A is a positive number, different from 1, so a is positive, right? Now, first thing is, first property or first interesting fact is that the domain. So what would be the domain of this function f? Well, the domain is my input x can be any, I mean, it's not a division here. And of course, we won't have a negative number under like a square root or something, right? Because my a is positive. So my input x can be any real number, okay? So then the domain would be just the whole number line, okay? So my x, the input x can be any real number, can be any real number, all right? So then the domain, the set of inputs would be just the whole number line. So the domain is just negative infinity, positive infinity. Okay, so you don't have to exclude anything from the domain. Now, what about the range of exponential functions? Well, the range is because a is positive and we have a to the power x, right? So this a to the power x would be also positive. So so the range, the outputs, the set of outputs actually would be just the positive numbers. So because a to the power x is because a is positive, then a to the power x is going to be positive. Okay, so my output f of x, so then the range would be just a positive number. So the range, so then the range is just positive numbers. It cannot be 0. Okay, so I have to exclude 0 because we have to exclude 0 because a to the power x cannot be 0, right? We have to exclude 0 because, well, when you do a to the power x and a is not 0, then a to the x cannot be 0 because a to the x cannot be 0. Okay, that's because, again, a is positive, right? Now, the x-intercept. What about the x-intercept of this function exponential in base a to the power x? So next property, the x-intercept. So x-intercept, remember guys how we find the x-intercept? We have to solve f of x equal to 0, right? That's how we find the x-intercepts. So my f of x is the exponential in base a, right? So that's a to the power x equal to 0, but a cannot be 0, so this a to the power x cannot be 0. So there is no solution because my a is positive. There is no solution, because the only way to have 0 is when a is 0, right? 0 to the power x, that will be 0, but otherwise you cannot have 0, right? So there is no solution because a is positive. So positive number to some power, it cannot be 0 because a is positive. So if there's no solution, so there's no x-intercept. So there's no x-intercept. There's no x-intercept. So it means that you cannot intersect the x-axis. So no intersection. The graph of, so the conclusion is that the graph of a to the power x do not intersect the x-axis. So the graph of a to the x do not intersect the x-axis. Right? That's because there is no x-intercept. Now, what about the y-intercept of this exponential function? So for the y-intercept, so we have to evaluate f of 0. So of course, your f of x is a to the x, right? That's my f of x, my exponential on base a, right? So we have to evaluate f of 0. So that will be a to the power 0, right? You plug 0 in the. No problem, Samira. Thank you for letting me know. Thank you. So f of 0 is a to the power 0. So a to the power 0, because a is non-zero number. Non-zero number to the power 0 is just 1, right? So then your y-intercept, if you have an exponential function in any base a, the y-intercept would be just so 1, right? So intercept is 1, right? Anyway, so this is like the main properties of any exponential function. The domain is any real number. The output is just positive number. There's no x-intercept, and there's y-intercept at 1, right? So for example, if let's say you want to graph, just to give you an idea about the graph of exponential functions. So I mean, in this section, we are not really interested in graphing exponential functions. What's really important for us, it's solving equations involving exponential and logarithmic functions. But let me just give you an idea here. So for example, let's say you have f of x, 2 to the power x. So this is an example. Right, so 2 to the power x. We said, I mean, you can make a table with values of f of x. So this is f of x, that's 2 to the power x. For example, x is 0, 2 to the power 0, that will be 1. X is 1, 2 to the power 1 is 1. 2, x is 2, 2 to the power 2 is 4. 3, you're going to have 8. 4, you're going to have 16, etc. So you see here, your function f is actually, it's increasing, right? All right. But anyway, so then if you try to graph this 2 to the power x. So let's say this is 1, 2, 3, etc. So we said 2 to the power 0 is it's 1, right? Then 2 to the power 1 is 2, 2 to the power 2 is 4, 2 to the power 3 is 8. So it's actually an increasing function, right? And then it's increasing, so the 2 to the power x would be something like this, right? So this is my 2 to the power x. So it's increasing, and also, as I said, your graph is not supposed, of course, this is 1 here, 2 to the power 0 is 1, that's your y-intercept. But yes, so the graph is not supposed to intersect the x-axis, right? So here there's no intersection. So the graph and the x-axis, they don't intersect. So there's no intersection here. So in some sense, your x-axis would be like a horizontal asymptote for this exponential function. Okay, so that's, again, there's no intersection because there's no x-intercept, right? So so what I'm saying is that in general, the x-axis, like here, x-axis is a horizontal asymptote for exponential functions. Right. Anyway, so this is just give you an idea about the shape of the graph of exponential functions. Any question, guys? Yeah, as I said, we are not really interested in graphing exponential functions. What's really interesting for us is the next, which is the logarithmic functions. So, you know, the thing is about this exponential functions is that they have inverse, and that will be the logarithmic functions. So, logarithmic functions. So the the definition of logarithmic function. So the logarithmic function, they are just the inverse of exponential functions. So let's say you need x to be positive. So for x positive, so this is really important condition here. You need your x to be positive. So the inverse. So the inverse of the exponential function a to the x. So the inverse of this function a to the x is logarithmic function is g of x equal to log. So this is the definition of log, right? The definition of log is the log is defined as the inverse of the exponential. So this is log in base a of x. All right. And again, you need your x, this x here, to be positive. Okay, so this x has to be positive. So let me just remind you what's the definition of the inverse function. So remember, guys, g is the inverse of f. So just to remind you the definition of the inverse function. So f is the inverse, or g is the inverse of f, is the inverse function of f of x if we said f of g of x is equal to x, and g of f of x is equal to x, right? That's the definition of the inverse function, right? Now, I'm going to apply these two, this definition to the log and the exponential, right? So, so the consequence of this so my f of x, in our case, my f of x is a to the x, and my g of x is log in base a of x, right? That's my f and my g. And g, the log, is supposed to be the inverse of the exponential of a to the x, right? So now, if you have, so f of g of x is equal to x implies So my f is a, so a of g, so the power would be log in base a of x. So then that will be equal to x, okay? So this is like our first identity, right? That's like the relation between the exponential and the logarithmic function, right? So of course we need the same base, right? So a to the power log in base a of x, that will be x, right? And that makes sense because exponential and log, they are supposed to be, so the log is supposed to be the inverse of the exponential, right? So in some sense, this is your exponential and your log, like they cancel out. So it's like saying f and g, they cancel out, and then you end up with just x, right? That's our first identity, right? Now the second one, if you have g of f of x equal to x, so the second identity would be a consequence of g of f of x is equal to x. So this one here implies, so my g is supposed to be log in base a of what? Of f. My f is the exponential, so that's a to the power x. And so that is also equal to x. So this is like our second identity, right? So we have two identities. I'm gonna just erase the. So this is a. So this is a log in base a of x is equal to x, and the same when you start with the log and then you have exponential, so they cancel out, then you get x, right? So you have to keep in mind that these two. So you have to memorize these two identities, right? This one here and this one here. So for example, let's have some examples, right? So so how can I use these identities? So in examples, so let's say examples. Okay, so in the example, I want to solve, let's say for x. I want to solve for x. Okay, so first example. So let's say I have log in base 6 of x is equal to 3. All right, and I want to solve for x, right? I want to get x, right? So so the problem here is the log, because we have log of x. So we have to keep in mind, guys, you cannot separate the log of the x. This is not log times x. This is log of x, right? So your log needs some variable, right? So it's log of something, right? So this is log of my x. Now I want to get rid of this log, right? I want to solve for x. I want to get rid of the log. So the idea here would be to get rid of the log is to apply exponential. So the idea. So you apply exponential to both sides. And so why do we apply exponential to both sides? Because then your exponential and your log, they would cancel out, right? So because exponential applied to the log, right, they would cancel out. Okay, so if you have exponential of a log, because the exponential is supposed to, or the log is supposed to be the inverse of the exponential. So then whenever you have exponential of a log, they would cancel out. So in our case, I'm gonna apply exponential. Now, what would be the base? Well, here I have log in base 6, right? This is base 6, all right? So I'm gonna apply exponential base 6. So here's my exponential base 6 equal. So on the right side, I have this 3. So here I'm gonna put power 3. And the left side, I'm gonna put this power. So the power would be this log in base 6 of x, right? So that's what I mean by applying the exponential. So I have my exponential base 6 to the power, and in the power, so this is a power here, right? And the 3 is also a power. It's not 6 times 3, it's 6 power 3. It's not 6 times the log, it's 6 to the power log, okay? So now we have the 6 to the power log. So this one here, this would be like your exponential in base 6, and this is like your log in base 6. So exponential and the log, because they are inverse of each other, they cancel out. So then you're gonna have just 6 on the left side equal to 6 power 3, which is, I guess, 36 times 6. 36 times 6, that would be 260, right? If I'm not mistaken. So then your x is 216, right? So you see the idea, guys? You have a log, you want to get rid of the log, just apply exponential, because exponential log, they're inverse of each other, so they cancel out. Another example, this is example number 1, example number 2, and then I'm going to give you an exercise. So example number 2. So now let's say you have 2 to the power x equal to 9. Right? And of course, the goal here, you want to solve for x, right? You want to find x, solve for x. Solve for x. So what do we have here? We have this is 2 to the power x, so this is like exponential in base 2, right? This is exponential in base 2. Exponential in base 2, right? I want to get my x, so to get the x, I want to get rid of the exponential, and to get rid of the exponential, of course, we have to apply log, right? So apply log. To get rid of the exponential. All right, so I'm gonna apply log both sides, of course. Wherever you apply to the left side, you have to apply the same thing to the right side. So we're gonna have log. Oops. So we're gonna have log in base 2. That's 9. Sorry, Elisa. This is you mean this? That's 9. Sorry, that's 9. So I'm gonna apply log base 2 both sides. So here's my log in base 2. Here's my log in base 2. There's an equal here. So I'm gonna put the 9 on the right side, and I'm gonna put this 2 to the power x on the left side. Right? So I just apply the log on both sides. And again, the idea is that this log and this exponential base 2, they cancel out because they are inverse of each other. So then you end up with just x on the left, and on the right, that will be log in base 2 of 9. And that will be the answer. So you see, guys, how I solve for x? You have an equation with the exponential, apply the log. You have an equation with the log, apply exponential. So then you can get, you can solve for x. Any question, guys? This is a 9, of course. 9. All right, so here's an exercise. Very small exercise. So we need to solve for x. Solve for x. All right, so first you have, let's say, log in base 5 of of x. This is supposed to be x is equal to 3. All right, and then second equation is So we have 7 to the power x is equal to 50. All right? So you have a couple of minutes, guys, to solve for x. Am I recording this session? Yes. Okay, perfect. Okay, any guess for number 1? Samira? Yes, 125. Yes, absolutely, 125, number 1. Yes, very good. Yes, very good, correct, Samira. Yes, number 2, that would be, absolutely. So I'm gonna give you 1 more minute, guys. All right, I guess so for number 1, we have this log in base 5 of x equal to 3. Right? You want to solve for x. You want to get rid of this log. So I'm going to apply exponential. My base here, this is base 5. So I'm going to apply base 5, exponential in base 5. Here's my equal sign. So on the right side, I have 3. So it's going to be 5 power 3. Left side, I have this log in base 5 of x. So that will be 5 to the log in base 5 of x. Now, this exponential in base 5 and this log in base 5, they cancel out. So that will be just x on the left side. And it's 5 cubed on the right side. And that's 125. All right. So number 2. So it's a 7. So 7 to the x equals to 50. Of course, if you had like 7 to the x equal 49, then x would be 2, right? So because 7 squared would be 49. But here it's not 49, it's 50, right? So it's anyway. So the left side, this is an exponential in base 7, right? This is exponential in base 7, right? Exponential in base 7. So we have to apply natural log to get rid of the exponential, and the same base, of course. So we're going to have log in base 7 on the left side and log in base 7 on the right side. Okay, here's my equal. It's 50 on the right side, and on the left side, it's 7 to the power x. So then the log and the power, the log and the exponential power 7 cancel out. So that'll be just x on the left. Right, and then this is on the right side, that would be log in base 7 of 50. All right, so that would be the answer. Okay, any question, guys? So yeah, so you see this relation between the log and exponential. So I mean, the main idea is just to play with these two identities, right? The log of exponential of x would be x, and the exponential of log of x is x. Anyway, yeah. So one more thing. Before the properties of the log. So let me just say, guys. Remember, I talked about this special number e. So when the base, the base, so your a is equal to this number e, which is we said, you know, it's approximately 2.785, I think, and we said this is a special number because the exponential is going to be equal to its own derivative. So so your f of x, your exponential function is e to the x, right? But then the inverse, the log, then g of x, which is the log in base e of x, this is called a natural log, ln of x. Okay, so it has, when the base is e, this special number, so we say we call the log natural log. So it's a natural log. It's because it's natural. It's natural in physics in some sense. Okay, so this is ln. So this is a natural log. Okay. So this is ln. N, right? And so when you say ln or natural log, that's just the log in base e, where e is this special number. All right. Anyway, yeah, now we are interested in the properties of the log. So now, so properties of the log. Log in base a of x. Okay, so first property is that log f of 1, which is log in base a of 1, this is always 0. Okay, log of 1, it's always 0 because you know, you can just try to solve the equation, but the reason is you know, if you apply exponential both sides, so then you would have a to the 0 is equal to 1, right? So yeah, so just keep in mind f of 1, log of 1 in any base is 0. Okay. 2, f of a, so that's the log in base a of a. This is always equal to 1. Okay. So for example, if you have example, if you have you know, log in base 3 of 3, that's equal to 1, right? Or natural log of e is equal to 1. Okay, natural log, that's the log in base e, right? So yeah, so log in base a of a is equal to 1. That's because, again, you can just solve the equation as we did in the previous exercise, and you will get 1, okay? Now, next important, very important property is that log of a product, if you have log of x times y in base a, that's a log in base a of x plus log in base a of y, okay? So all I'm saying, guys, here is that, so log of a product is the sum of the logs, okay? So for example, so let's say you have log of 15, log of 15 let's say in base, wherever base, so let's say base is 4. So that will be, because 15 is 3 times 5, right? So then that's a log of 3 in base 4 plus log of 5 in base 4. All right, so keep in mind, log of a product is the sum of the logs. Okay, log of 15, that's a log of 3 plus a log of 5 in the same base, of course. All right. Now you may ask, what about division, log of x over y? This is number 4. So now if you have a log of let's say log of x over y in base a, then that will be the difference between the two logs. So that's the log in base a of x minus the log in base a of y. All right. So for example.
Wait, sir.
Yes.
The number 3, the example, is the addition or is multiplication?
Yeah, the number 3, we said here log of 15. So 15 is a multiplication of 15 is 3 times 5, right?
Okay.
So yeah, I'm saying like log of 3 times 5, it's log of 3 plus log of 5.
Oh, okay.
Mm-hmm. Now, now we have a division, though, then there will be the difference between the logs. So for example, let's say you have log in base 5 of 1 over 7. Okay, so we have this division fraction 1 over 7. So then that will be the difference between the logs. So it's log of 1 base 5 minus the log of 7 in base 5. Right? So if you have a division, then that will be the difference between the logs. And here, because you know, because log of 1 is 0. Remember, guys, we said here, we said the log of 1 is always 0. So this log of 1 here in base 5 is 0, right? So then that will be actually 0. So that will be 0 minus log in base 5 of 7. So that's negative log in base 5 of 7. Right? Because log of 1 is always 0. All right. And last and also important, very important, important property of the log. So number 5. So if you have log in base a of x to the power b. Okay, so you have x to the power b. So it's like x times x b times, right? Then because actually that's a consequence of number 3. But then if you have log of x to some power, then what you can do is you can bring down this power here in front of the log. So this b here goes here in front of the log. So that will be a b times log in base a of x. All right, so you can bring down the power b in front of the log. Okay. So for example, examples. So let's say you want to solve for x. All right. So let's say you have 2 to the power x equals to 1 over 8. Okay. So let's say this is our first example, example 1. Well, then first we said, so this is an exponential in base 2, right? This is this is exponential in base 2, so we have to apply a log, right? This is exponential in base 2, so we have to apply, the log in base 2 to both sides. So I'm going to have a log in base 2 on the left side and a log in base 2 on the right side. And so you're going to have 1/8 on the right side, and you're going to have 2 to the power x on the left side. Now, we said the log and exponential, they cancel out. So this log and this exponential, they cancel out. So it's just now it's just x on the left side, right? So we're gonna have x on the left side equals to log in base 2 of 1/8. Now we can try to simplify this, right? Because we have all these properties of log. So first, this is 1/8. So this is a division. It's a fraction. So that will be the log of the difference between the logs. So it's log in base 2 of 1 minus log in base 2 of 8, right? That's because log of a fraction, that will be the difference between the logs, right? And then we said log of 1 is always 0. So this log of 1 here, this is always 0. So so that will be equal to 0 minus, so that will be negative log in base 2 of 8, right? But then we can also write 8 as 2 to the power 3, right? 8, this is minus log in base 2. So log in base 2. 8, it's 2 cubed, right? So then, remember guys, we said if you have this, this log of x to the power b, then you can just bring down this power b in front of the log, right? So here I have this log of 2 cubed, so then I can move this 3 here in front of I can bring it down in front of the log. So that will be to, that's equal, there is a minus, bring down the 3 in front of the log. So there is my 3 times my log in base 2 of 2, right? But then log of in base a of a, that's equal to 1, right? We said, remember, that's the second property, or where is it? Yeah, a second number, no, a second property. We said log, see here, log of a in base a is 1. So for example, log of 3 in base 3 is 1. Here we have log of 2 in base 2, right? This is this is equal to 1. Log of 2 in base 2, that's equal to 1. So then the answer would be negative 3 times 1. And so your x is actually equal to negative 3. Right, so you see guys how I use all these properties to solve for x. So my equation was 2 to the power x equal to 1/8, but then using the log and to get rid of the exponential, and then I use these properties of the log, like log of 1/8, that will be the difference between the logs, log of 1 minus log of 8, and then etc., etc. So then the answer is actually x equal to negative 3. All right. So here's an exercise, a similar exercise. So we have to solve for x. Solve for x. Oops. So solve for x. So number 1. So let's say you have number 1. So you have, let's say 3 come on, 3 to the power x equal to 1 over 81. Okay. Number 2. Number 2, so we have, let's say, 2 to the power x equals to, let's say, 5 over, let's say, 8. Okay, so please try to solve for x. And of course, try to simplify your answer. Okay, solve for x and simplify it. And simplify your answer. Yes, correct, Kwame. Very good. For number 1, yeah. Okay, so any guess for number 2, guys? Um, yes, Samira, you can do that with a natural log. Yes, that's one possible answer. Absolutely, with a natural log. Yes, yeah, absolutely. We can also just apply. We can also apply a log in base 2. Yeah, I mean, actually, there are different ways actually to solve but yeah, but your answer is correct. Yes, absolutely. All right, so okay, so for number 1, guys, so you have this 3 to the power x equals to 1 over 81. So we said this is exponential in base 3. So I'm going to apply log in base 3 to both sides. Sorry, this is my log. Come on. Oh, sorry. So this is log in base 3. So here, this is 3 to the power x, and this is 1 over 81, right? So then we said log in base 3 and this exponential in base 3, they cancel out. So it's going to be just x on the left equals to this log base 3 in base 3 of 1 over 81. But the thing is, as I said, you have to simplify your answer. So this is, it's 1 over 81, so it's a fraction. So then that will be the difference between the logs. So it's the log of 1 in base 3 minus log of 81 in base 3, right? And then we said log of 1 is always 0. So this log of 1 is always 0. So that will be, so x would be minus log in base 3 of 81. Now, 81 can be written as a power of 3. So that's actually 3/4. So this is, so you have x minus log in base 3 of 3/4. And so 81 is a 3 power 4. And so then you can bring down this power 4 in front of the log. So that would be x would be negative minus 4 times log in base 3 of 3. But then log in base 3 of 3, log in base a of a is always 1. So this is always equal to 1. So then that's negative 4 times 1. So your x is just negative 4 times 1. So x is negative 4. All right? Any question, guys? Okay, very good. So then we can move to number 2. It's 2 to the power x. Good. So then 2 to the power x, 5 over 8. So number 2. So we have 2 to the power x, 5 over 8. right? So as I said, I mean, there are different ways actually to solve this equation, but this is exponential in base 2, right? And you want to get rid of this. You want to get rid of this exponential in base 2. So I'm going to apply log in base 2 both sides. So here's my log in base 2. Here's my log in base 2 both sides. So this is 2 to the power x, and this is 5 over 8. So, and then this is log and exponential, they cancel out. So your x would be just, so your x, it's just log in base 2 of 5 over 8. But this is a fraction, 5 over 8. So you can, that will be the difference between the logs. So it's log of 5 minus the log of in base 2 of 8. All right. But then, well, you cannot really write 5 as a power of 2, but you can write 8 as a power of 2, right? 8 would be 2 cubed, right? So then your x, would be log in base 2 of 5 minus log in base 2 of 2 cubed, right? So then you can, move this 3 in front of the log. So then that will be x is equal to log in base 2 of 5. And again, as I said, the 5, you cannot really write 5 as a power of 2. But then minus 3 log in base 2 of 2. But then this, of course, log in base 2 of 2, that will be equal to 1. This is equal to 1. So the answer here, one possible answer would be that your x is equal to log in base 2 of 5 minus 3 times 1. So x is log in base 2 of 5 minus 3. All right, so that's one possible answer. You can also write this in terms of a natural log. So if you prefer, you can write this in terms of the natural log. Yes. Any question, guys? Okay, perfect. So then, okay, now we're gonna solve some equations. Okay, so now we're gonna solving logarithmic and exponential equations. So I'm gonna start with the logarithmic equations, exponential equations. So I'm going to do a couple of examples, guys, to show you how to solve first logarithmic equations in general. So examples. So example number 1. So let's say I have log in base 4 of x minus 1 plus log in base 4 of x plus 5 equals to 1, right? And of course, I want to solve for x, right? So this is a logarithmic equation because we have logs in the equation, right? So in general, we said if you have a log in an equation and you want to solve for x, so then the idea would be to apply exponential, right? But the thing is, there's a problem here is that we don't have only one log, we have 2 logs, right? So the first step to solve such an equation would be to combine all the logs in just one log. Okay, so you combine all the logs in one log, and then you get rid of the log by using the exponential. So step one, I'm gonna combine these two logs. So step one would be to combine all the logs in just one log. Okay. So the question now, of course, is how can we combine these two logs in just one log? But remember, guys, we had this property of the log. We said a log of a product would be a sum of the logs, right? We said this is, so just to remind you, one of the properties of the log. So we said like log in base a of x plus log in base a of y. That would be log of x times y in base a, of course. Right? So in the equation, we have log in base 4 of x minus 1. So this x minus 1 would be like my x here, and this x plus 5 would be like my y. Okay, so then log of this x minus 1 plus this log of x plus 5, that will be log of the product, log of x minus 1 times x plus 5. Right? So what I'm saying, guys, is that so this log of x minus 1 plus log of x plus 5, that will be log of x minus 1 times x plus 5, right, equals to 1. Right? Again, so this is like, here's like, this is like my x, log of x. This is like, sorry, yeah, this is the y. So log of x plus log of y, that will be log of x times y. Okay, now I combine the two logs in just one log. Now I can, so of course, this is a log in base 4, the same base, right? Now I have only one log, and that's good news because now I can get rid of this log using exponential. So step 2 would be to apply the exponential to get rid of the, as usual, as we did in the previous examples. So step 2, apply exponential to get rid of the log. So this is a base, this is log in base 4, base 4. So I'm gonna have 4 here. Here's my 4. This is equal. So on the right side, I have 1, so that will be 4 to the power 1. It's not 4 times 1, it's 4 to the power 1. Left side, that will be 4 to the power, this log in base 4, this x minus 1 times this x plus 5. All right? Now, this 4, this exponential in base 4 and this log in base 4, they would cancel out as usual. So on the left, that will be just x minus 1 now. So it's x minus 1 times this x plus 5 equals to 4. So you see, guys, I had two logs, and then I combined them, and then I applied my exponential to get rid of the log, and so I end up with some, this is just a quadratic equation, right? So because if you expand, x times x, x times 5, 1 times x, and then 1 times 5, so there'll be, x squared plus 5x minus x minus 5 equals to 4. All right, so then you can here subtract 4 both sides. So we're gonna have x squared plus 5x minus x, that's plus 4x, minus 5 minus 4, that's minus 9, equal to 0. Okay, so then this is just a quadratic equation, so I can use my quadratic formula. So it's minus b minus 4 plus or minus square root of b squared, that's 4 squared, that's 16, minus 4 times A times C. C is negative 9 over 2A times 2 times 1. All right, so then this is minus minus, that would be a plus. 4 times 9, that's 36. 36 plus 16, that will be 52. So we're going to have x equals to negative 4 plus or minus square root of 52 over 2. All right. So then you're going to have two solutions. 52 is not a perfect square, right? I mean, 7 times 7, that would be 49, and 8 times 8 is 64. So it's 52, it's not a perfect square. But anyway, you can just keep it. So we're going to just keep the square root of 52. So it's minus 4 plus square root of 52 over 2. And x is minus 4 minus square root of 52 over 2. Okay, so we got two possible solutions because there is one more step. We are not done yet. I know it's a bad news, but yeah, so we are done. We are not done yet because we have to make sure. Remember, guys, we said for the log, we only apply log for positive numbers, right? So if you have a log of something, then it has to be a positive number. So what I'm saying is that if you have so this log of in base 4 of x minus 1, so your x minus 1, this x minus 1, oops. So this x minus 1 must be positive. So this x minus 1 must be positive. And this x plus 5 also must be positive because we have log of x plus 5, and you can only apply a log on positive numbers. So this x plus 5 must be positive. Okay, so actually there are two conditions to check. I need my x minus 1 and my x plus 5 to be positive, right? So here I have these two possible solutions. So I have to check in this last step, step number 3, we have to check the conditions on x. So step 3, check the conditions on x. So what we are saying is that x minus 1 and x plus 5, they must be they must be positive. Okay. So let's first solution. I got this one first possible solution. I got this this negative 4 plus square root of 52 over 2. So I need to check if x minus 1 and x plus 5 are positive. If they are both positive, then that will be a final solution. Okay. If x minus 1 or x plus 5 is not positive, then I have to reject the solution. So that x wouldn't be a solution. Okay. So if let's start with x negative 4 plus square root of 52 over 2. So that will be approximately, if you use a calculator, square root of 52 is approximately 7 point something. So 7 point something minus 4, that will be plus 3 point something over 2, that will be approximately 1.5 something. Okay. Then if you do x minus 1, then x minus 1, which is 1.5 minus 1, is going to be positive, right? And if you do x plus 5, of course, going to be also positive, right? So then if x is this -4, so if this x is -4 plus square root of 52/2, then x minus 1 and x plus 5, both are positive. Come on, both are positive. Okay, so then, so conclusion is that then this is a solution. Then -4. So this -4 plus square root of 52/2 is a solution. So this is a solution. Now, what about the other one? So if x is -4 minus, you said 1 is negative? What do you mean, Elisa? But the 1 is negative. So I am saying this x with the plus square root of 52 would be, oh yeah, so yeah, you put x minus 1. So, but x is 1.5 approximately. So this x would be 1.5, right? So I'm trying to check if this number here, this one here, if you subtract 1 from this, okay, if you subtract 1 from this number, then it's still positive. And that's the case because, so what I'm saying is that this -4 plus square root of 52/2, that's approximately 1.5. So then if you do 1.5 minus 1, so think of this x as 1.5, right? This is, so if you do 1.5 minus 1 or 1.5 plus 5, both, they're going to be positive, right? 1.5 minus 1, that would be 0.5, yes. So yeah, I'm trying to check if for this number, right, if you subtract 1 or if you add the 5, if that would be positive. And yes, that would be positive. Now, if you do -4 minus square root of 52/2, that's approximately, I guess, this is 52, of course. Sorry, this is 52. All right, so square root of 52, it's 7 point something minus 4, that's like -11 point something. So that will be over 2, that will be -5 point something, okay? Let's say -5.5 or 0.6, let's say 0.5. So then if you do -5.5 minus 1, that will be -6.5, right? Or even if you do plus the 5, it's going to be also negative. But anyway, if one of them is negative, so like this -5.5 minus 1, that's -6.5. So this is negative. So then you have to reject. So the solution, so then x equal to -4 minus square root of 52/2 is, so this solution is actually rejected. Right. So it's rejected. So a final answer, we would have only one solution. So final answer. All right, so the only solution is actually x equal to -4 plus the square root of 52/2 is a solution, is the solution. Okay, so that's the only solution of our problem. Again, guys, that's because you can only apply log to on positive numbers. So you have this x minus 1, you have this x plus 5. So if you end up with some solution which is says that the solution -1 or the solution +5 is negative, then you have to reject the solution. Okay. Any question, guys? All right. Okay, so this is when we have a plus, right? This is, I had, log. So let me just remind you the original equation. We had this log of x minus 1 plus this log of x plus 5, right? Now, if you have minus, so this is example number 2. And then I will give you an exercise, guys, okay? I promise. So example number 2. Oops, what happened? All right, I just lost my board. Okay, something weird. All right, well, anyway, so example number 2. I think there is a problem with the Zoom today. Anyway, so for example number 2, I'm gonna have log in base, let's say 2 of x plus 1 minus log in base 2 of x minus 3 equals to 2. Okay. So this is different from the previous example, guys, because in the previous example we had the plus. Here we had the plus, right? But in this example we have minus, right? So this is different from the previous example. So, but the idea, the steps, they will be the same. But the first step, we said in the first step, we need to combine the logs into just one log, right? So here I have these two logs. Now the question is, how can I combine these two logs in just one log? Well, but here the thing is, again, this is a minus. So then, so just to remind you, if you have a difference between two logs, so if you have log of x in base a minus log of x, log of y in base a, so then if you have a minus, so then that will be the log of the quotient. So that will be log of x over y. Okay. So in the step 1, again, we have the same. So step 1 would be, again, to combine the logs in just one log. One log. But then here, I don't have a plus, so it won't be a product. I have a minus, so it's going to be a quotient, right? So then we're going to have log in base 2 of my x. That's like my, this x here, that will be like this, my x plus 1, and y would be this x minus 3. So it's going to be x over y. So it's going to be x plus 1 over x minus 3, right? Equals to 2. So you see, guys, difference between if you had the plus or minus between the two logs. If you had the plus, then it should be log of the product. If you have a minus, then there'll be log of the quotient, right? Now, okay, so now we had just one log. That's the first step. The second step, get rid of the log as usual by applying the exponential, right? Apply the exponential to get rid of the log as usual. So then this is a log in base 2. Right, so I'm going to apply exponential in base 2. So here's my 2. Here's my 2. Right. Now the right side, I have a 2, so it's going to be 2 power 2 on the right side, and on the left side I have 2 to the power. So the left side is log in base 2 of x plus 1 over x minus 3. So same idea. So this is. So this exponential in base 2 and this log, they would cancel out. So it's going to be just x plus 1 over x minus 3 equals to 2 to the power 2. That's 4. So you see, guys, here I don't get like a quadratic equation. I get like a fraction equal to some number, right? So then how can I solve this equation? Well, the idea is you have a fractions. So I'm going to make the right side look like a fraction. So I'm going to divide by 1. I mean 4. That's also 4 over 1. It's the same thing. And so what we do when you have two equal fractions and you want to solve, then we can just cross multiply. Okay, so it's like x plus 1 times 1 equals to x minus 3 times 4. All right, so then that's x plus 1 times 1, so it's just x plus 1. And the right side, x times 4, that's 4x, minus 3 times 4, that's 12. All right, so let's say you subtract x both sides. So it's 1. 4x minus x, that's 3x minus 12. And then we have plus 12 both sides, plus 12. So that's 13 on the left equals to 3 over x, 3x. I'm going to divide by 3, both sides. 3 over 3 cancel out, so it's just x now. So I got this possible solution, which is x equals to 13 over 3, right? Now, still, we have this last step. We have to check if my log is applied on positive number. So this is step 3. So we have to check the conditions. So what are the conditions here? I need my logs to be applied on positive numbers. I have, so the original equation, I have this log of x plus 1. So I need to check that, I need to make sure that this x plus 1 is positive, and I need to make sure that the x minus 3 is positive. So my solution is, so to check the conditions, so the condition is that, so x minus 1 and x plus 3 are positive. Again, because log is only applied on positive numbers, right? So this x plus 1, sorry, x plus 1 and x minus 3. So this is, sorry, this is, should be x plus 1 and x minus 3. This is x minus 3, of course. So both of them are positive. So my solution is 13 over 3. So I have to check. So is 13 over 3 plus 1, is it positive? Yes, obviously, right? Now, is 13 over 3 minus 3, is it positive? Well, I mean, 13 over 3, it's like, it's 4.33, right? 4.33 minus 3, it's 1.33. So yes, it's also positive. So both of them are positive. So then that's a final solution. So then answer, we're gonna have answer. So 13 over 3 is a solution. Okay. Guys, if you answer no to one of these two questions, so if you say no here or no here, then actually the solution here, the set of the solution is empty. There will be no solution. Okay. If you say if your 13 plus over 3 plus 1 is, let's say for some reason, is negative, all right, so then you have to reject the solution, and so the answer would be there is no solution. Okay. So both the x plus 3 and x minus 3, both of them must be positive. If one of them is negative, then you have to reject the solution and there will be no solution. Make sense to you guys? All right, so here's an exercise. I know it's a lot, so here's an exercise. So I guess next time we still have, I guess next time I will continue with this, but let me just give you an exercise, and then we'll continue with this next time. Okay, an exercise. So please solve for x. So two equations. So first equation, you have log in base 3 of x minus 1 plus log in base 3 of x plus 2 is equal to 2. All right. And number 2, you have log in base 5 of x minus 4 minus log in base 5 of x plus 3 is equal to, let's say, 1. All right. So please try to solve for x. I mean, we have like 5 minutes. I know we don't have time to go over this exercise today, but anyway, I guess I will go over this exercise next time. But I'm gonna give you 5 minutes, guys, to think at least about the first equation. So again, right, guys, so just to remind you, so we won't meet this Wednesday because this Wednesday we will follow Friday schedule, right? So next time I guess I'm gonna see you next. I will see you next Monday. Okay. Yes, Elisa, we don't have a class on Wednesday because Wednesday will follow Friday schedule. So if you have like a class on Friday, like in the usual time, you have a class on Friday, so then you would have a class on Wednesday. So again, it's because it follows, Wednesday is gonna follow Friday schedule. So if you have a class on Friday, you would have that class on Wednesday. And of course, Thursday and Friday are holidays, right? So. Mm-hmm. And by the way, guys, I wish you happy holidays, right? Happy Thanksgiving.
Yes, happy holiday.
Thank you. You too.
Happy Thanksgiving.
Thank you. Thank you, guys.
Happy Thanksgiving, everyone.
Thank you. But yeah, yes. So basically, we have only like 2 lectures left. Next week, we're gonna have 2 lectures, and after that, we're gonna have the test and then the review for the final. So it's like only 1 week left, and then we're gonna have just the test and the final. I see there are some questions. Oh yes, for the test, yeah, sure, I can post the review sheet. So I'm gonna do it this week. The test is again, it's December 7th. right? So it's like in 2 weeks, right? So I will post the review sheet as soon as possible. Yes, yeah, Recklin, yeah, I will do that. Yeah, I promise. I will do my best. Sure. Yeah, enjoy your holidays, Alexander, of course. All right, guys, probably I'm gonna stop here because there's only 1 minute left, but anyway, so I will come back to this next. You can think of this exercise, of course, if you have time. But I will come back to this next Monday. All right. So again, happy holidays, everyone. Enjoy your Thanksgiving and stay safe and take care. All right. Thank you, everyone. I will see you next Monday. Thank you, guys.